we're going to be looking at chemical changes. There is quite a lot of content in here that might be just on higher only or on separate signs only. So remember, if your exam is highlighted in green, that means you could be assessed on it. However, if it's greyed out, this is content that's not on your specification and will be not included. We're going to start by looking at metal reactions first of all, before we move into making salts, titrations, and then electrolysis. So first of all, with metal oxides, we need to be aware that the majority of metals are going to react with oxygen. And when they do, we're going to have a metal plus oxygen forming a metal oxide. So for example, iron and oxygen will make iron oxide. Aluminium plus oxygen is going to make aluminium oxide. In this process, the metal is being oxidized because oxygen has been added on to the metal. We have two types of reactions to be aware of. Oxidation in terms of oxygen is when oxygen is gained by a substance in a chemical reaction. So for example here, the metal is being oxidized. Oxygen is being added on. There is also, however, a reduction reaction, and this is when oxygen is lost. You might sometimes notice a phrase of redox reaction, and this is a reaction in which there is something been oxidized, so gaining oxygen, and something's been reduced, losing oxygen. But in this scenario, we've just got an example here of an oxidation reaction. Still linking into these metals, we have the reactivity series, and this is the idea that some metals are more reactive than others. Now you'll notice the majority of these are metals, however there are two non-metals present here. We've got carbon and a bit lower down hydrogen. So as a general overview, when metals react, they're going to form positive ions. They tend to lose electrons as they turn from metals into ions in reactions. But how likely they are to do this, or the ease at which this happens, is related to their reactivity. So potassium, for example, an alkali metal, loses one electron very, very readily, while aluminium loses its three outermost electrons less readily, so it is less reactive than potassium. So the higher the tendency of losing their outermost electrons, the more reactive that substance is. Notice the position of carbon, it's below aluminium. So we've got first of all our group 1 metals, then our group 2, and then our group 3 of aluminium. Carbon goes underneath, and everything else below this are transition metals. So they're found in that middle kind of block of the periodic table. We have decreasing reactivity as we go down, and right at the bottom we've got gold. So we've got carbon placed below aluminium and hydrogen placed above our copper or below our lead. So what we tend to find is that we can use this to model displacement reactions, because a more reactive metal can displace and take the place of a less reactive metal from a compound. So for example, if I have iron sulfate, so iron is here, and we add zinc, zinc is slightly more reactive than iron, and so it will take iron's place. The iron has been displaced. And this is all down to the fact that zinc is more reactive than the metal that was in that compound already. A displacement reaction is a reaction in which a more reactive element displaces or pushes out a less reactive element. And you might be asked to predict if reactions occur based on reactivity. If, for example, we'd added lead instead, which is way less reactive than iron, this wouldn't be able to displace because of the fact it's less reactive than iron itself. So if we have a look at each of these, would there be a reaction and why? So if we have potassium oxide and carbon, potassium's up here, carbon's down here. Potassium is more reactive than carbon, and so there will not be a reaction. So if potassium is more reactive, carbon cannot displace it. And so no reaction will occur. Literally potassium oxide and carbon will go in, potassium oxide and carbon will come out. In the next one though, we've got magnesium sulfate, so magnesium's here, and we add sodium. Now here there will be a reaction because sodium is more reactive than magnesium, and so it can displace it. So we'll write our equation. We'll have magnesium sulfate and sodium going in, and now our sodium and magnesium will swap places, so we'll have sodium sulfate and magnesium coming out. In the next example, we've got aluminium sulfate, so aluminium's here, and we add lithium. Now there will be a reaction here because what we see is that lithium is more reactive than aluminium, and so it can displace it. So here we'll have aluminium sulfate and lithium, and we'll make lithium sulfate and aluminium. In the next one, calcium sulfate, and we add magnesium. Now here there'll be no reaction because magnesium is less reactive than calcium. It can't displace it. So we'll just have these two chemicals come back out of the reaction. No reactions occurred. As an exam question, you could be asked to write a method to possibly figure out the order of reactivity of these elements. With this, what we can do is we can get these metals and we can react them with either water or acid and make observations. So if we get a fixed volume of acid, for example, so like 50 centimeters cubed, we can add a fixed mass of the metal to this. We'll give it a stir, most likely using thermometer. It comes in double handy here. And what we'll do is we'll record the greatest temperature change that we measure. We can, if we want, repeat this with water also. And we can then do this with different metals. So we can add different metals to fixed volumes of acid and water and measure the temperature change. The rule here is that the more reactive the metal is, the greater that temperature change will be. So we can physically measure that temperature, getting a quantitative value, and have a really clear idea of which was the most reactive to which one was the least. An alternative is you could look at the bubbling. However, that now gets far more descriptive, and so you're not going to be able to assign a value to that. So I'd much rather say we're going to measure our temperature change when we add a fixed mass of metal to a fixed volume of acid. What you tend to see though is that potassium, I wouldn't actually recommend adding to acid. It will react incredibly quickly with acid and very quickly with water. Even with water, we're going to see that bright purple flame and loads of fizzing. Sodium, again, you wouldn't react this with acid, and you'd see a very fast reaction with water. Not so much as potassium though. Lithium will still react very quickly with acid and will have quite a violent reaction with water. This is where you'll see that fizzing, skimming along the top of the water. These metals you would not be adding to acid. Water, fine, not an acid though. And that's because they are so reactive. Calcium and magnesium, you'll see quite a fast reaction with acid, and still with calcium, a very fast reaction with water. Magnesium will still react quickly with acid, but it won't react as quickly as calcium did. It is less reactive. And by the time we get to zinc, it will have a slow reaction with acid and a reaction, if at all, with water. Iron will be small or very slow, and again, it's going to rust really slowly. You probably wouldn't record a temperature change there either. And copper won't react with acid, and it's not going to be reacting with water. Now, where this reactivity series links in is the idea about we can use our knowledge of the reactivity series to be able to extract metals from their ores. Now, ores are rocks that contain minerals or metals in a high enough quantity that it's worthwhile or economically viable to remove that metal and extract it. Now, some metals, such as gold and platinum, for example, are so unreactive they are found exactly as they are in the Earth's crust. So we find these as pure metals. But for example, iron, tin, lead, aluminium, we're going to find that these are found as metal oxides within ores in rocks. So most of these are going to be compounds and will require reactions to extract them out. Now, the way in which we extract them depends on where they are on this reactivity series. So some metals can be extracted using carbon, and we can use carbon to displace them out of their ores. So carbon, as I've mentioned, is a non-metal found below aluminium. So all of these metals below carbon, so zinc, iron in particular, tin, lead, copper, they can all be extracted from their ores by actually reacting with carbon and reducing them, so removing the oxygen from them. If, however, the metal is more reactive than carbon, this is where we need to use electrolysis, and we'll talk about this a bit later on in the session. So if we have a look, for all these metals below carbon, what we can do is extract them using carbon in displacement reactions. So for example, zinc oxide plus carbon, we're going to make zinc and carbon dioxide. This is possible because carbon is more reactive than this metal, and so it can displace it. So in this example, zinc has been reduced. It has had the oxygen removed from it. Carbon, however, has been oxidized because it's gained oxygen. So this is both a displacement reaction, but it is also a redox reaction. We've had both reduction, zinc has lost oxygen, and oxidation because carbon has gained it. As a bit of higher content here, there are two definitions for oxidation and reduction. One is about what's happening in terms of oxygen. The other is what's happening in terms of electrons. Now, oxidation can either be when oxygen is gained or when electrons are lost. Reduction then is when either oxygen is lost or it can be the gain of electrons. A way of remembering this is oil rig, and this stands for oxidation is loss while reduction is gain. So this is in terms of electrons what's happening, and it's worth mentioning there might not even be any oxygen in the reaction, but if we've got a loss or gain of electrons, we can have oxidation and reduction also. Now if we keep along that line of looking at the Ionic equations here, if we look at this, we've got a copper sulfate and magnesium, and our magnesium is displacing the copper. We're getting magnesium sulfate and copper coming out. Now if we focus on this in terms of the ions, we've got our copper, our sulfate, our magnesium, atoms in this case, and we've got magnesium ions coming out, sulfate ions still there, and copper. Now notice the sulfate ions are just there on each side of the equation. These are known as spectator ions. They're not actually involved in the reaction, they're just there. So we can remove them out of the equation. Now if we focus on these two halves for higher, what's actually happened here is that the copper ions have gained 2 electrons, turning back into copper, while the magnesium has actually lost 2 electrons to form these magnesium ions. This copper has gained electrons, it's been reduced, while magnesium has lost electrons, so it's been oxidized. And this would be an example of a redox reaction with both reduction and oxidation occurring. In the next section, we're going to start to look at the reactions of acids and start to look at salts. When we look at the reaction of acids, acids and metals react together to form salts plus hydrogen. And as this occurs, it is a redox reaction because both oxidation and reduction will occur. Metals can react with acids, but acids are also able to react with bases. And when they do this, they're going to make salt and now water. We've got a couple of different bases to be aware of. Examples of bases can include metal hydroxides or can include metal oxides as well as carbonates. And these are any chemical that can react with an acid in a neutralisation reaction. So if our bases are either metal hydroxides or metal oxides, we're going to make a salt plus water. However, if we also have a metal carbonate as our base, then we will, on top of our salt and water, also make carbon dioxide as another third product. If we have a look, in this example, I've got my base magnesium oxide reacting with hydrochloric acid. Now I'll make a salt and water, and the salt here will be magnesium chloride because of the base and acid in which I've used. In the next example, I've got magnesium carbonate reacting with nitric acid. Now, because this is a carbonate, I will still make a salt and water, but I will also make carbon dioxide. Because we've got magnesium carbonate reacting with nitric acid, our salt will be magnesium nitrate. So the first part of that salt's name has come from the base, and the second part of that salt's name has come from the acid. In our next example, sodium hydroxide and sulfuric acid will now make salt and water, and our salt will be sodium sulfate. The next base is copper oxide reacting with hydrochloric acid. So we're going to make a salt and water, and the salt will be copper chloride. Lithium carbonate now reacting with an acid means we'll make a salt and water, but we'll also make carbon dioxide, and the salt's name will be lithium chloride. Our final one, we've got sodium hydroxide and nitric acid. Now this base will make a salt and water when it reacts with an acid, and the salt's name will be sodium nitrate. As general key terms, an acid is any substance that can produce hydrogen ions when in solution, while an alkali is a substance that can produce hydroxide ions when in solution. So acids produce hydrogen ions, alkalis produce these OH- ions. A base is any substance that can react with an acid and neutralise it. So an alkali is an example of a base. Neutralisation is a reaction in which an acid reacts with a base to make salt and water. If that base is a carbonate, it means we'll also make carbon dioxide. The pH scale is a way of measuring how acidic or alkali something is, and we'll look at this in a moment. Now we need to be able to describe how to make salts. And with this, we're going to add an insoluble metal oxide or carbonate to an acid. A common mistake that people make is they'll just refer to adding a metal, but forget it needs to be a metal oxide or carbonate. But whatever we are adding needs to be insoluble, which means it will not dissolve. If we use a hydrochloric acid, we'll make a chloride salt. If we use sulfuric, we'll make a sulfate. And if we use nitric acid, we'll make a nitrate. So for example, if I want to make copper sulfate, I could either use copper oxide or copper carbonate. So in this one, I'll use copper oxide, and my acid, I'll have to use sulfuric acid. When we go to make a salt, there are lots of steps involved with this. So the first thing is we need to add the insoluble base in excess, so too much of it, to warm acid. We give this a stir, and once we're satisfied that no more base will react, we will then filter that solution. What we will then do is we'll pour that filtrated solution into an evaporating dish, and we will then warm this gently over a water bath. So this beaker being heated by a Bunsen burner is acting as a water bath, preventing from this being heated too strongly. As soon as we start to see crystals appear, we stop heating this and turn the Bunsen burner off and allow this to crystallize slowly over time. One thing that might happen is you might be asked to explain how we make sure this is a pure salt, in that we just get the salts that we want to make and nothing else in there. So the first thing is about the fact that base is added in excess. This ensures that all the acid must have reacted. Now we add the base in excess because we can filter this out at the end, while if we had too much acid left over, you wouldn't be able to remove it because it's soluble. So the base is added in excess to make sure all the acids reacted. Now with this, we'll use a warm acid and we'll stir, again, just to increase that rate of reaction and really ensure that acid is fully gone. The filtration then removes the insoluble base. So what this should mean is at this point here, all we've got is the salt in water. All the acid was gone because the base was added in excess, and the base is now gone because we filtered it out. In the next bit, we are now removing the water. So in this evaporation and crystallization section, we are removing the water from this. And so by doing this, what we should leave with is just the crystals. Now we turn the heat off because crystals thermally decompose if they're heated too strongly. So we need to make sure that these grow almost slowly and they are cooled slowly. The drying process, you could even, as this gets to the point of nearly being finished, you can blot it dry with filter paper. You can put in a warming oven around 30 degrees and allow to dry slowly at a relatively low temperature. But this process will ensure that all of the water is removed while getting these large crystals form. When an acid reacts with a base or when an acid reacts with an alkali, we're making salt and water, and you might be asked to explain why this happens. Now, acids are substances that form hydroxide ions when in solution, while alkalis produce hydroxide ions. pH can be measured in a range of different ways, but one that we'll look at is universal indicator. So this is a chemical that we can add a few drops of and observe the colour change to try and match it to a colour chart to give a close assessment we can about the pH of a substance. So once we've added that universal indicator, we'll need to refer to a colour chart and use that to identify which pH we've got. The issue here is our perception of colour can be subjective, and so you might have two people looking at the same results and disagreeing on if it was pH 11 or 12, for example. Now the colour this turns does tell us a lot about the substance. So if it's going red or orange or yellow, we know it must have a pH below 7. We are now looking at it is an acid. If it's red, it's going to be pH 1 or below, so 0. If it turns green, that's going to be neutral, will be a pH of 7. While if it's turning blues, it's relatively like pH 10, 11 for an alkali. Or if it's going into the purples, we know it's probably now strong alkali at pH 13 or 14. But there are other indicators. So litmus is another one. We can use, and you have to use them together, red and blue litmus. So we dip red and blue litmus into our test solutions and we observe the colour change that happens to them. So if they're dipped into neutral solution, what we'll find is that they will both just stay the colour that they were originally. If they're dipped into an acid, both the ends should come out red, while if they're dipped into a base, both the ends should come out blue. So what this is very good at doing is telling us is it acid, alkali or neutral, but it doesn't tell us the pH of the substance. So if my acid, I'd have no idea if that's pH 1 or pH 6, for example. The only one I'd be really aware of was neutral. I'd know that's pH 7. But for acids and bases, I'd know it had a pH less than 7, but I wouldn't know what that would be. Well, if I got my positive result for a base, so 2 blue ends, I'd have no idea what pH that was above 7 all the way up to 14. Another way that we can get quantitative data is using a pH probe, and this will give us an actual number of the pH. So it removes this issue about the perception of colour being subjective, and you can get some with quite a high resolution that can read to 2 decimal place. A very common 3-mark question is to be asked why water is produced during neutralisation. Now it's about the idea that acids make hydroxide or hydrogen ions, alkalis are making hydroxide, and when these react, our hydrogen ions plus the hydroxide ions make H2O of water. You might be asked to write this equation and you'll be given a good couple of marks for it. It does tend to cause a bit of anxiety when it gets up in the exams when you're asked to write an ionic equation for neutralisation. But if you are ever asked to do this, this is all they're wanting you to do, to show that hydrogen ions plus hydroxide makes water. They might occasionally ask you where the ions are coming from, and I would write my equation and just label that acid. I would label this base or alkali and making water. So we're seeing where those hydrogen ions are coming from, where the hydroxide are coming from. For the next short section, we'll be just looking at how we carry out titrations, and this is only in separate science. Now, titrations can be used for chemical analysis, and within your chemistry paper, you'll very much be looking at how to determine the concentration of a substance. Now, we're relying on this idea that alkalis neutralize acids, and what's happening is during this neutralisation reaction, the hydrogen ions from the acid react with hydroxide ions from the water, and exactly that point of neutralisation, we have got all those hydrogen ions bonded to hydroxide ions with not too much hydrogen or too much hydroxide. What we will tend to do is use an indicator to figure out the point of neutralisation. Now, we will not use universal indicator here because that has a range of colours. We'll use a colour or an indicator with a distinctive colour such as phenylalethene, which will either be one colour if it's asteralkali or another if it's not. So we'll have a very clear endpoint on this. So we have to follow a standard procedure for this, and it's just to make sure we've got reliable data that we can use to actually get some valid results. So what we'll tend to do in your titration questions, be prepared for having one substance that you know the concentration of and another that you don't know the concentration of. And what we tend to do is we will measure a fixed volume of one substance that we normally don't know the concentration of into a conical flask. And we can use a pipette to do this. So we'll add our acid or base, 25 centimetres cubed, with a pipette to the conical flask. We use the pipette because it's very good at measuring fixed volumes. And this will be the substance that we don't know the concentration of, typically. What we'll then do is add our indicator, swirl this to make sure it's mixed, and we'll place this down on a white tile. We will then fill the burette with the other chemical, and this will be the chemical that we do know the concentration of, but we want to see the volume we need to add to get this to neutralise. Now we use a burette here because burettes are really good at measuring variable volumes. So what we'll then do is we'll add the chemical from the burette to the conical flask. And as we know we're getting to the end point when neutralisation is near, we'll start to add this drop by drop. So we'll add a drop, swirl it, place it on the white tile. Another drop, swirl, place on the white tile. And we'll measure the volume used from that burette to get that exact point of colour change of our indicator. What we should then do is repeat this at least 5 times, and what you're looking for is 3 concordant results that are within 0.1 of each other. So to make sure this is precise, accurate and repeatable, we need to make sure though we've done these repeats, but to have a good idea about where we need to start adding drop by drop, before we do our real titrations, we'll normally do what's called a rough titra first. So this is a very quick run through where we get a quick idea of right, at what point will this turn colour. And it then lets us know when we then go to do this for real, at what point should I really be starting to add this drop by drop? Because we'll know the point it's changed colour, it'll give you a good idea of right around this volume I need to start adding it a little bit more at a time. So we need these readings that we do get in our results and our repeats to be really close together. They might refer to these as concordant results, but they will be within 0.1 of each other. So it does mean that any that aren't within the 0.1, you discard as outliers. Now back onto content that's on both the combined and separate science but higher only, we've got this idea of strong acids. Now, strong acids are completely ionized when in solution. So what this means, for example, if I've got hydrochloric acid, the hydrogen ions in their entirety dissociate and separate from the chloride ions. Now, examples of strong acids that you would use in a lab are hydrochloric, nitric and sulfuric acid. These will tend to have pHs of around 1 to 2, and you might be asked to estimate within your exam. Weak acids, however, are only partially ionized in solution. So what this means is that sometimes the hydrogen ions are dissociated from the rest of the substance, but sometimes they're not and they're attached. What this means is that weak acids have far fewer hydrogen ions in solution and therefore are not as acidic. So weak acids will tend to have pHs that are higher, from pH 4 up to pH 6, for example. Ethanoic, citric, carbonic acids are all examples of these. So strong acids completely ionize in aqueous solutions, while weak acids only partially ionize. If we refer to dilute acids, this is one where we've got a higher proportion of water compared to the solute. Now, if we've got a strong acid, even if it's dilute, it will still have a low pH. A concentrated acid is one in which we've got a smaller volume of water. Now, even if I've got a concentrated weak acid, they are still not going to have pHs below 4. The reason for this is that the measure of pH is all down to the concentration of hydrogen ions. So the higher the concentration of hydrogen ions, the more acidic and the lower the pH a substance is going to be. While if something's got less hydrogen ions, it'll have a higher pH. Now, what this does mean is that there is a relationship. What we'll find is that if you've got a weak acid and a strong acid, even if they're the same concentration, the strong acid that's completely dissociated from its hydrogen ions will have a far higher number of hydrogen ions in solution. They are going to have a lower pH than the weak acid that hasn't released as many. But one thing to be aware of, and it starts to get into maybe a 1 marker but very much a grade 7 to 9 question, is about the effect of increasing the concentration of hydrogen ions on pH. So for the pH to fall by 1, you need to have 10 times more hydrogen ions. So if I wanted to get from pH 6 to pH 2, for example, I would need times by 10, times by another 10, times by 100, times by another 10, so that'd be 1,000, times by another 10, 10,000 times more hydrogen ions to get to pH 2. If I wanted to go from pH 4 to pH 5, I'd need 10 times less hydrogen ions. Back onto content that's on everyone's exams, we're going to have a look at electrolysis. Now, this is a way in which we either will have molten or dissolved ionic compounds, but what they both have in common is that the ions are free to move, and as a result, we're going to have a flow of electricity. Now, the molten or dissolved ionic substance is the electrolyte, and what will happen during electrolysis is an ionic compound is broken down into the simpler substances, and we'll look at a few examples of this as we go through. So if we have a look, we've got our electrolyte, which is either molten or dissolved, so added to water. We have a power supply and we have wiring that connects to our electrodes. Positive ions will be attracted to the negative electrode that's called the cathode, while negative ions will move to the positive electrode that we call the anode. The anode is another name for the positive electrode. The cathode is our negative electrode, and electrolysis is the process by which ionic compounds are broken down to simpler substances using electricity. And the electrolyte is the substance that's broken down. This will be an ionic compound that's either been melted or dissolved. One that's specifically mentioned in the specification is about lead bromide. So if we've got the electrolysis of lead bromide, lead ions, the metal ions, are positive, and so they will be attracted to the negative cathode. So the lead ions will actually here gain electrons and they'll turn into lead. Over at the anode, the bromide ions are negative, and so they'll be attracted to the positive anode, and the bromine will be made at this one. If we have a look, if we've got these molten ionic compounds, they're quite simple with molten compounds to predict what's going to be made. The metal will go to the cathode, the non-metal will go to the anode, and we literally just split these in half. but be really careful reading the questions. You need to highlight if it's molten or dissolved or in solution, because that will depend on what you say is your answer. But in these, they're all molten. So at the cathode, I'll make zinc, and at my anode, I'll make chlorine. For the next one, lithium oxide, well, I'll make lithium at the cathode, well, oxygen at the anode. And we carry on in this way. So notice my molten ionic compound has been split into two simpler substances. So here my copper has been formed, and then oxygen. Sodium chloride is broken down to sodium and chlorine that goes to the anode. And zinc bromide will be zinc and bromine. As a safe precaution, because the halogens in particular are toxic, if you know that you're going to produce these gases, or even lead for that matter that's also toxic, it's well worth making sure that you're doing this in a fume cupboard if you've got access. Now we can use electrolysis to extract metals, and this is when we've got metals that are more reactive than carbon. So it means that if they're more reactive than carbon, we can't displace the metal from its ore in a displacement reaction using this carbon, but we can break it down with electricity. Now the downside of electrolysis is that you're going to have to melt your rocks, which is going to take a huge amount of energy, and secondly, you are also going to have to use electricity that also has a cost. So electrolysis is more expensive for both the energy that's needed to melt these substances and the energy that's needed for the actual electrolysis process itself, because we need an electric current. Now, aluminium is the big one that we extract through electrolysis. With this, we first of all have molten aluminium oxide that we mix with a chemical known as cryolite. Now, cryolite turns this into a mixture and lowers the melting point of aluminium, or the aluminium oxide, I should say. The benefit of this is we've got a lower melting point, and therefore not as much energy is needed to melt this ore. So this cryolite has reduced the melting point, therefore reduces the energy or cost of this process. The other thing to be aware of is that the electrode here is made up of carbon. So in electrolysis, our aluminium ions, which are positive, will be attracted to the negative electrode and here are discharged. The aluminium ions will turn to aluminium, they'll be hot, they're melted, but they'll then be piped off. However, the oxide ions are negative and they'll be attracted to the positive electrode and form oxygen. But this container is incredibly hot, we're talking hundreds of degrees. And so the oxygen will immediately react with the actual carbon in this electrode, and it will form carbon dioxide gas. So as this reaction is going on, the electrode burns away because it reacts with the oxygen that's been made there to make CO2 instead. What that does mean is the anode will change in appearance and will need to be replaced over time. It will physically get smaller and smaller and smaller. Now, for higher content only, be prepared to explain what's happening at each of these electrodes. So if we look at the positive electrode first of all, oxygen ions or oxide ions are attracted to the positive anode. And the negative ions will lose their electrons. And because of this, oxidation is lost, they are being oxidized. And our equation for this is we'll have our two oxide ions losing their electrons, they've lost 2 each, so a total of 4, and they'll make an oxygen molecule. Now, what will be amazing in your exam is if you're confident writing that half equation as it is. But if you know that actually I'm not quite secure as I want to be, this is what I'd have on a flashcard and learn, for this is what's happening with oxygen during electrolysis. And it won't change. So if electrolysis and half equations of oxygen come up, this will be what they're looking for. But what happens here is the oxygen then reacts with the carbon in the anode to make carbon dioxide gas. So oxygen and carbon will make CO2, and this happens because of the carbon in this electrode. Now, the negative electrode, now positive aluminium ions are attracted to the opposite charge. Here, they're going to gain electrons, and what we know is reduction is gain, they are reduced. So for example, my aluminium ion will gain 3 electrons. Notice the number of electrons it gains is linked to its charge to form aluminium, a solid metal. Or if this is a hot temperature, actually, it'll be liquid until it cools. But this will be our half equation for what's happening with our metals. If we go back on to content for everyone, so including foundation. So far I've looked at the electrolysis of molten, but there can also be the electrolysis of aqueous solutions. So this is where we've added water and dissolved it rather than melted it. Now both of these scenarios involve ions being able to move freely. But in this one, the products made is a little bit more complicated. So the rule about aqueous solutions is that oxygen will be made at the anode unless it contains a halide. Now a halide is anything in group 7. So if you notice you've got chlorine, bromine, iodine, they will still be made at this electrode, but nothing else will be. So it can only be a halide, or if it's not one of those substances, oxygen will be made. Now at the cathode, the rule is here that hydrogen is made if the metal is more reactive than hydrogen, and most metals are more reactive than hydrogen. The only metals that I've seen come up on the exams that are less reactive will be your copper or possibly silver. So for most aqueous solutions, what we'll see is that hydrogen will be made at that negative electrode. The only exception is that copper and silver are less reactive, and so if they're present, they'll be discharged first. Now the reason for this is because of the fact that when we've added these into solution, we've added water. And what happens is the water splits off into hydrogen ions, which is why they get attracted to this cathode, and hydroxide ions, which are negative, which is where this oxygen is coming from. So when we add water, what we're doing is adding hydrogen ions and hydroxide ions that could get involved with electrolysis itself. So oxygen will be made because hydroxide ions go over to this electrode and get discharged, unless there's a halide, in which case they'll go instead. But in this side, my hydrogen ions will go and be discharged, and they've come from the water itself. So we now have aqueous solutions, and we need to ask ourselves as we're going through, is it more reactive than hydrogen, and is it a halide? So zinc is more reactive than hydrogen, so we'll make hydrogen. This is a halide, so we'll still make chlorine gas. In the next one, lithium, yes, that's more reactive than hydrogen, so we'll make hydrogen. And oxide, no, it's not a halogen, but it's also oxygen, so we will make oxygen at the anode. For the next one, potassium fluoride, well, potassium is more reactive than hydrogen, so we'll make hydrogen. And what we find is that fluoride is a halogen, so that'll be made at the anode. Copper sulfate. Copper is less reactive than hydrogen, so actually copper will be discharged first, so we will still make copper. Sulfate is not a halide, and so we'll make oxygen at the anode. For sodium chloride, sodium is more reactive than hydrogen, so we'll make hydrogen, but chloride is a halogen, and so we will make chlorine. And for the last one, zinc bromide. Zinc is more reactive than hydrogen, so we'll make hydrogen, and bromide is a halogen, and so we'll make bromine here. The key when you're looking at these questions, if you're asked to predict the product, is make sure that you've highlighted, was it molten or was it in solution? If it was molten, just split the elements down. But if it's in solution, be aware you could now have hydrogen or oxygen made too. For the higher content only here, be prepared to explain what's happening at the cathode and anode, not just for aluminium oxide, but for each of the reactions they give. But the common thing is that negative ions will be attracted to the positive anode. They will lose their electrons and be discharged. So the negative ions, because they've lost electrons, are oxidized. So for example, chloride will have 2 chloride ions go. each lose one electron to form chlorine. This half equation you could use for any of your halogens. So again, if you're not too confident with your half equations, you can write them on a flashcard, but if you know you're one for one of your halides, you know it for all, because actually you can swap this out with an F and do it for fluoride, or you can swap it out for Br and replace it for bromide. It'll be the same half equation for each. And oxygen we looked at earlier. Now the positive ions are attracted to the negative cathode. Here they will gain electrons and so are reduced. Now writing our metals does tend to be a bit more straightforward. We write the metal and its charge, add in the electrons that equal the charge of the ion, and show the metal coming out. So, for example, chlorine. This will be formed at the anode, and here we'll have our chloride ions to make chlorine and 2 electrons, because each of these chlorides have lost an electron each, and they've been oxidized. So they've lost electrons. Aluminium will be made at the cathode because of the fact it was positive, and here my aluminium ion will gain 3 electrons and form aluminium. It's been reduced, it has gained electrons. Copper 2, and the copper refers to its charge, will also be made at the cathode. So there's my copper 2, and it's gained 2 electrons to turn into copper, and it's been reduced. Now bromine, this will be made at the anode, and it'll be down to 2 bromide ions, each going across and releasing 1 electron each to form a bromine diatomic molecule that's paired up, and this will be oxidized. Fluorine, notice, another halogen does exactly the same thing, just we've got the F's rather than Brs. Hydrogen's the only one that's a little different of our positive ions. So this will be made at the cathode, but hydrogen again is diatomic, so we'll need 2 hydrogen ions going in. They will each gain 1 electron to make H2, and they've been reduced.